Hello everybody, we're back for part 3, types of lasers today. So let's bring up the board with some of the information here, start here. How is everyone today? I'll flip it over, say hi, good morning or afternoon or evening, or good morning for tomorrow if you're in the far parts of the world. Hello, Menru, nice to see you. And Chuck, hello. Saw like everybody came in very quickly. I didn't catch everybody, but good afternoon anyway. Hi, Music Monkey, how is everyone? David, hello. So Laura, nice to see you as well. So today we're going to talk about lots of different types of lasers that are used. Hey, Chuck. Including Scott actually asked me yesterday about the white laser. There was a white laser news. There was some news of a white laser that came out, so we'll talk a little bit about that and what that means. Tasha, nice to see you, girl. Thank you so much for that shout out, by the way. Hey, Mike. My favorite hairband. It's a very nice, Ollie. Very nice. I like that one. Hi, Heidi. Nice to see you as well. Ashley's in here. Oh, goodness. We got a good crowd. Okay, great. So, today, first things first, thank you. First things first, I'll do a quick plug because I completed my NAND band. So connection has been a bit buggy. Of course, thank you, Sam. Please, yeah, connection, I think with the updates and everything, you know, they're still working out kinks. So everybody, thank you for the patience and catching the replays if you do. So I'm glad it's good so far. So here is my NAND band. If you don't know what a NAND band is, and you don't know who Linda is at Connie Caps, I don't catch these, but I do save them. I'm just very slow at uploading them to YouTube because it takes a while, but I do record each of these with the comments. So even though they're not up yet, maybe, thank you, Ashley. I do have them, David, so thank you for asking. So they will be eventually up on YouTube, and I'll upload these, the laser sections, all three together, as a chunk, but I do save them with the comments, so they do still exist. They're not lost forever as far as with the comments go, so it doesn't look like I'm just completely talking to myself. So yes, of course, thank you for asking. And anyone who's new here, my name's Julia. My handle here, I'll turn it around one second. You have a laser. That's excellent. You want a headband? Well, you can make yourself one. So I'll talk about that in just a second. So my name is Julia. I'm here at Fine Woman on Twitter also. So feel free to tweet me because I have my my other device here at the ready. Should you want to send me a question there, if that's easier. If I don't see yours, you can email me or you can check out this page that gets very slowly updated, but it does have a link to the YouTube page, and then I will add the links that I'm going to talk about today that I've talked about yesterday as well. So. Another, hello, why is it so difficult to miniaturize high-power lasers? Great question, and I will definitely get into that briefly. So, oh, I'm sorry, hi Victoria, I'm sorry it's spotty. So yeah, please catch the replay if it's spotty. I'm on the Wi-Fi, Periscope's just kind of having issues lately. So quick plug, if you do not follow, I'm going to write her name down, Linda at Connie Caps. If you have ever had any interest in crafts, and you know, I actually, even as a physicist, personally, I really have a lot of interest in, gosh, anything really, a whole spectrum of things, and I don't think that just because someone is something in their career path or their main interest that they don't have other interests, and I think crafts is really one of, thank you, Connie Caps, yes, crafts is certainly one of mine, and Linda's just one of the sweetest women, so there you go, at Connie Caps, and she gives lessons on knitting, and she's just so sweet, or you can just kind of hang out and listen to her, very soothing, but she has this wonderful project where she's sending these NAND bands to children in a hospital in Brazil, and this took me maybe an hour and a half to make, and she'll teach you how to do it. So that's a fun project, and I wanted to plug that for her for sure. So you put two together. Yes, yeah, you can put them together. Always wanted to ask you, but fine. It's spelled, so yes, it's Fine Woman. I missed the end of that, Mike, I think, but if you're asking, so that comes from Richard Feynman. Richard Feynman is the author, excuse me, of this book. And hey, Linda, just there she is. So that's at Connie Caps. You can follow her right there. She says, hi, Julia. And then she has a show every day where she does a quick she'll teach you how to make different patterns of these. They're really simple, and they're going to go to a good cause, and they're fun. And you can learn how to knit. So, did you know each other? Yes, actually, Linda and I've known Linda for quite a while in Periscope world terms. So, this is Feynman's original lectures on physics, or from Caltech, and Richard Feynman's a physicist. He got a Nobel Prize in physics, actually, and that's kind of where handle name comes from, and to explain that. So let's, without further ado, because I don't want to, I don't like taking up too much of people's times. I know there's so many things to watch. So thank you. Thank you so much. And hold on, Org, I have to say, I look up your, see, and I look it up every time and I don't know your first name, and that's why I keep forgetting it, but thank you, Org. So it is, thank you, it's clever. It's clever if you know who Richard Feynman is, which I realize most people don't after I actually kind of got the handle everywhere, but so be it. Thank you so much. Oh, that's so sweet of you to say. All right, so let's talk lasers, because we've had 2 parts so far on lasers. We went through kind of the basics of what lasers are, how they're different from Oliver. Thank you, Oliver, for telling me. So we went through some of the basics on how they're different from regular, for instance, incandescent light bulbs, and the inner workings then we got into yesterday, and kind of the quantum mechanics, a little bit of the math. Try not to make it too intimidating or out there, so exactly, pew pew. So we're going to talk about pulsed lasers, actually. No problem, Ashley. Thank you for listening. And pulsed lasers are a little different than what they call CW, constant wavelength, or the lasers that are always on. And even when you're looking at them, it's hard to tell. So the pulsed lasers have such short pulses, and they're happening so often that to our eyes, it looks like it's always on, but it's actually not. So we're going to talk about a number of different types of lasers that there are out in the world that are being used. Everything from diode lasers in laser pointers to high power, what they call petawatt lasers. And there's actually a news article today I tweeted that is talks about in Japan, they've now claimed they've made the most powerful, which is a 2 petawatt laser, which actually I haven't seen it. I haven't seen the Lexus hoverboard. So the 2 petawatt laser kind of doubles the power of the 1 petawatt laser, which happens to be at the University of Texas, and it happened to be, the facility was actually right underneath and next door to my office and lab that I was working in as an undergraduate at University of Texas. So that's really exciting to see. So I'll flip this around. We'll show you some really cool pictures, because that's much more interesting to look at. Okay, so we'll draw some pictures here if we need to, but for right now, we are going to go to some of these pictures. The first thing, so the different types of lasers, when we talked about, a little bit yesterday, when we talked about the ways, actually I will draw a picture here really quickly, sorry. So we talked about the cavity of a laser, and I'll just maybe briefly review for people who didn't see it. The cavity of the laser is, these are mirrors, and we have some material here. And this material here, I'll just write material, because it can be anything, and that's what makes these different lasers. And, well, let's see, mirror. And then what happens is we get this light, right, from the atoms or the molecules within the material, and one of these atoms is going to emit that nice wavelength, and then stimulate the guy next to him to emit the same wavelength at the same time with the same phase, etc. So we go back and forth. So that's a brief review just of yesterday, so or and the day before. But without getting too much into that to take time, does light have a direction? Absolutely, and that is definitely part of what makes the laser a little different, because you end up here forming what looks like this. But you get lots of, oops, see, I'm not quite perfect on the drawing, but I'll do my best. So you get the idea, you get lots of them in this cavity here. And then what happens is, if this mirror here lets a little bit out, then you get a little bit of the power, and there's a tremendous power building up here. There's just, oops. There's a tremendous power building up in this cavity, and so when a little bit of it leaks out, you get this high power of light all in the same direction, and that is important, because unlike a light bulb, when you have a light bulb here, then what happens is that filament, right, that gives off light in all different directions. And so that then takes that power, but spreads it over all different directions. So the light here is going to be in the same direction. Greetings from Canada. Hello. So this is actually a very good point. So thank you for asking, because that is what makes the difference between laser light, for instance, and one of the differences, and incandescent or light bulb light. So the material here, that's the key part. I just wanted to point out briefly, because the material, what is actually, so we talked about the atoms and the molecules and actually controlling the amount of energy, that very precise, those chunks of energy that they're going to have, and when they release that energy. And oh, sure, of course, please ask questions, everybody. Yeah, if I lose you or you don't understand, please, please, please ask me questions, because I absolutely would love to answer them, and chances are other people are going to be confused if you are as well. How is laser light concentrated? That's a great question. So we talked a little bit about that yesterday, and I'll put these on the YouTube. And the concentrated aspect of it is this cavity. So it's a mirror here and a mirror here. And so the light, this stimulated, right, this is what laser stands for here, this stimulated part is not only stimulated by one atom, you know, next to his neighbor, but we make many, many round trips, because the light that's emitted hits the mirror, bounces back, stimulates even more, and so we get, oops, that's, I gotta draw at least close to the same wavelength, right? So we get these guys coming out here, and then it hits the mirror and makes another round trip, and then that leads to this kind of standing wave picture, but this is just building up more and more power, and then that what leaks through, that's the concentration, what leaks through is the laser light. So that's kind of a brief, hopefully that sort of that made sense. But if there's a lot of people that are still kind of lost, I'd rather make sure people understand that. What laser light photons are perpetual? So great question, and actually, technically, all photons are perpetual. So perpetual meaning they will travel until they hit something. So that is a characteristic of light, and it is, again, the International Year of Light. And light will go on forever until it hits something. So that's kind of interesting to think about when you talk about the telescopes, the Hubble telescopes. The light that we capture to make those images it's light from these galaxies that has been traveling unhindered. Absolutely it does, Mike. Great question. I'll get to that in just a second. So all of this light traveling from these galaxies are completely unhindered, doesn't hit anything until bam, hits the telescope. That photon now is no longer a photon from the galaxy, right? It's now turned into energy of some sort to give us information of that on that picture. So the distance between the mirrors is absolutely true. It is vital, actually. It's vital to making this standing wave pattern for the color of light that you're going to get, for the material. And I think I showed a picture of the laser I was working with, and aligning these things is just so complicated sometimes, because it's amazing, Ellie, because this distance does have to be very, very, very precise. So how is light prevented from going the opposite direction? So it does go the opposite direction, and that's okay, because it's actually, do lasers work different in vacuum? It depends on the laser, because it depends on the material, really, but kind of the easiest answer is, in general, it's not a big deal. Vacuum you don't need. So most of the time you need vacuum is to protect these mirrors if you have very, very sensitive laser systems, but or to protect the material. But the light itself is, it travels a little bit differently in air, and you might have to take that into account in these very, very specific, sensitive systems. But typically, so for instance, you know, most of the lasers used in labs, etc. So for instance, this one works just fine in air, and that's not really a problem. So to answer that question, the cavity question, yes, these have to be very precisely placed, because that wave that distance, the wavelength has to build up in that cavity and has to be held well in there. So we'll work on your straight, yes. And so is that Scott? Did Scott come in here? So these are the really cool types of lasers that we've got. There's so many. There's so many. So there's something called a there's a diode laser, which uses actually, let me get the book out. Hey, it was you, Scott. So we're going to talk about that white light laser. No, what do you... great question. Yeah, so exactly, the lasing material. So it's those, whatever the atoms or the molecules are that you're controlling here in their energy states, because you're controlling each of these atoms and molecules. You're controlling how much energy they have, because they're going to release that energy in the same, they call it phase, right? So one atom is going to stimulate his neighbor to release the same exact energy at the same time. And so that amount of energy, that quanta, that chunk of energy, will be different for different molecules, different atoms, because of their structure. So the material, it's very dependent on the material. And that material can be anything from liquid, gas, crystals, and so here, I'll turn this around. So we'll go back to this book that I love so much. We'll look at the different types, just kind of a brief, I'll show some pictures here of the different types of lasers. So ruby laser was one of the earliest ones. So that actually uses a ruby crystal, because the energies that of the actual molecules inside the ruby they were able to figure that one out first, essentially, and how to control that and make that work and build that cavity such that you could build up this energy. So is everyone kind of with me? Is this kind of interesting? And if you'd like to hear about something else or want to ask more questions, please do. So I would, this is for you, for everybody watching. So I would love to make this interesting. I could talk about this all day, and all of it's interesting for me, but definitely would rather cater to everybody watching this. So I'll keep going until somebody interrupts me. So please feel free to do so if I lose you. So one of the other ways to do it, oh great, the other things to do is use a dye laser. Now, not many people use dye lasers anymore because it is exactly what it sounds like, a dye. It's a liquid dye. And, oh, wonderful, thank you. Yes, that's what I try to do. So if I kind of throw in words that you don't know, please let me know, and I'll try to find another way to explain it. So these dye lasers, that material we're talking about, is actually, it's going to be like a cell or something holding liquid, and that's liquid of molecules that you're going to get this specific light out of. Where is the current direction now in the search for good laser material? It's great. So it is so advanced. There are so many different types of materials. They're getting smaller, more complex. And actually yesterday when Scott brought up this white laser, then what they've done is they've taken, because as we said, so the material is going to determine the color of the laser, and that's the other thing that separates laser light from from light bulb light, or incandescent diffuse light. These are all words to kind of say the same thing. So the difference there is actually the color. You have one specific color because all these molecules or atoms, for instance, that are going to give you this light by releasing the energy at the same time, it's got to all be the same energy, because that stimulated process only works when it's the same energy. One photon, one little bit of light, that chunk of light that comes from one atom or molecule, is only going to stimulate and the same atom or molecule with this that's going to release the same energy. So exactly, how can laser light be white? It's a great question. So it's kind of non-intuitive. What they've done is they've actually, and I'll just turn around, I'll show you the paper, because I actually looked at the paper. And maybe it's interesting for people who aren't used to seeing what scientific papers typically look like and articles. So this article on exactly this. Let's see if I can zoom out a little bit on this one. And I think I have to do, does this work? Yes, excellent. Okay, so this is kind of what these scientific papers look like, and they can get very intimidating, even to me. I mean, I don't want to, some of this is like, gosh, I have to read all these, and you have to go through each of the captions here. The pictures are vital. So this is the actual paper about, and so what they've done is they've taken, this is the material, they've built the material, let's see if you can see this a little better. They've built the material to have lots of different materials stacked on top of each other. Now, that is very difficult to do, right? Because you have to have then a cavity, that those mirrors separating, just like my gas, those mirror separation having to be very specific to hold and support these very specific wavelengths. It's a complicated thing to do. So they've stacked these materials together, and they've built this cavity here. Too many of those wordy things. Oh, okay. So thank you, Sam. I'll slow down. So the cavity just describes this, or I should say this system here with one mirror and another mirror that kind of keeps that light bouncing back and forth and builds that power up. But those mirrors and the distance between those mirrors, that is very specific to the energy, which is the same thing as saying the wavelength or the color. All those mean the same things. Oh, the paper. Oh, okay, great. Oh, thanks. Okay, so yeah, so all of those mean the same thing, and so to support all those different wavelengths is very different, or very hard to do, and so they're using some clever magnetic tricks, etc. But what they've done is, instead of using one material, they're using many materials, and then each of the materials is going to give a different wavelength to make at the same time. Now, the big difference here is that this laser, turn around again. So this laser is actually constantly on. That's a little bit different because there are we can generate white light from laser systems, and we actually had one of these in the labs. We had three or four of these in the lab that I worked in as a grad student, where you can tune, they call them tunable lasers, where you're actually making pulses of light. And when you get to pulses of light, then instead of having that nice standing wave, it gets a little bit more complex, but you're actually putting lots of different colors on top of each other. And then where they constructively, so you can kind of think of frequencies like this, and I'll draw a picture in a second. But if the waves are the points of my fingers here, and you have two of them and they're a little bit different in separation, right? And you lay them on top of each other. If you lay them on top of each other such that just that central one is matched, then you get this huge peak power, but it's a very, very, very short time that it lasts at that huge peak. And that's that pulse that you want. But you have to do that with lots of different colors. So usually for a very short pulse of light, it's actually going to contain, it cannot, physics, that's actually the uncertainty principle. Physics dictates the fact that you have to sacrifice that one color aspect. You have to have a few more colors. Excuse me, I still cannot get rid of this cough. So yeah, that's actually a perfect emoji. You get a rainbow of colors all stacking on top of each other. And so let's see if I have a nice, I'll draw a picture too. Mama Panda, nice to see you. So here we go. My titanium sapphire laser, the cavity, and this is, I won't get too into the little details, but essentially the basics are you have one color like this, and then you have, for instance, I gotta draw this correctly, one color like, let me try that again. One color like this, and then one color like this. So you can see right here, that's where they're all stacking on top of each other, and what you end up getting is, right, some of these are going to cancel, and you end up getting something that looks like this. Oh, I can't draw. Oof, I'm sorry, I'm terrible at drawings today. So you get a peak. Excuse me. Oh, goodness. Okay, so I will get over this cold one day. So when I draw these axes, these lines, the reason that these two matter, actually, is because this is in time now. Are they harmonics? Great question. Excuse me. They are not, actually. They are not harmonics because the harmonics... I'm sorry, give me 1 second. Okay, so harmonics, great question. What do harmonics mean? Harmonics actually mean that you would have one frequency, and then you'd have exactly double the frequency. This is going to test my drawing skills. Let's see. So I need to have... Oh, I got close. So... Pardon me, everybody. Oh. And so the harmonics, harmonics, the doubles, that actually would not be good in this case because then you'd have them interfering constructively, adding on top of each other. Yeah, I need a cocktail. Adding on top of each other more places than just this central peak. And so that's not going to be as good of a process. Yes, I do. And I have some right here. So I'm trying to incorporate that, not dive on you. I have one. That's what I'm using, actually, Sam. I'm just not very good with it because I'm not a very good artist. It's exactly what I'm using now. So here, this pulse aspect, that's the cool part because then we have, let's say this is going to be red and this is going to be greenish, right? And this is going to be blue light. And what is white light? But white light is, oops, close enough. White light is all the colors mixed together. And that is how they can make these white light lasers, which is different than this. This is a little different. It is, oh, and I was going to show you this high power, this petawatt laser too, so that's really cool. But the, where's that picture? There we go. That white light right there is exactly, well, this is a similar process, but you can see what they're doing is spreading apart all those colors. So this is a beam of white light, which is really hard to do, and it's spreading apart. But actually what's happening is these are lots of pulses of light. So to our eye, it looks like a single continuous source, but it's actually pulses, very, very, very short pulses. And to give you numbers, just to make it a little bit more kind of awesome and awe-inspiring, hopefully, is that this pulse width here, how long in time, anyone want to take a guess at how quickly that it turns on and off? So I'll do a 0.0, and this will be seconds, so it's going to be 0.0000000. Okay, so we got 1/millionth. That would be 1/millionth of a second. No, 3. Yes, if I put a 1 there, that would be 1/millionth of a second because we have 6, right? 1, 2, 3, 4, 5, and then a 1 would be 6. Okay, getting closer. Nope. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the one I'm talking about, the laser that I worked with specifically. There's lasers that do pulses in pretty much this region and shorter. So 3, 6, 9, 10, 11, closer, 12. You have to add both of yours, Ashley. It's a millionth of a billionth. So 12, 13, 14, and we'll do a 15. So it's the 15th spot. So that's called 10 to the minus 15, which is a femto. Yes, exactly, Brazilian. Femtosecond. So that's what's called a femtosecond, and that's a millionth of a billionth of a second. And so that's why if you have a whole bunch of these that are only last that long, that you get to your eye, right? Your eye can't detect something like that. And interestingly, electronics can't even detect something like that. You have to use light and interfere with itself to actually measure how fast these pulses are. So, oh, they've gone past the screen. Oh, I'm sorry. Oh, I'm sorry. You're right. Sorry. There we go. So let's see. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14. Yep, 15. There we go. So, hey, Zebra, nice to see you. So that's how short in time these pulses of light are. It's a femtosecond. And picosecond would be 1,000 times smaller than that, or it's 1,000 times slower than that. And so that would be here. And that is actually what this, let's see, what this high power Japanese laser claims. So they do what's called a picosecond. Let's see, yeah, just 1 picosecond. If you can read that on, there we go, picosecond, trillionth of a second. So that is, and that's a lot of power. But the trick that they do here with the power is that power is energy over time. So the actual energy, and I really like this, I really don't like the way a lot of science articles are written these days, but this one is a good one. It's on Popular Science. And the reason is they actually quote the guy that works at the petawatt laser in Austin. So, and he says exactly this. He says the energy is about that in a cup of coffee, right? So that's not a lot of energy. But you're taking the energy of that cup of coffee and you're condensing it in time to that millionth of a billionth of a second. And so that's how you get a huge amount of, well, in their case, it's only a picosecond. Picosecond, come on, no, just kidding. But in that case, right, then you're condensing it into such a small amount of time that things that you're trying to study, that they shoot, right, it has to react so quickly because all that energy is so fast. So it's a huge blast, exactly right. And it's some strong coffee. Well, it's strong coffee is if you take all the energy of the coffee and instantly put it into your system, right? You have to react instantly. So, yes, so a quantum. So what do you, a quantum of what exactly? I like that word. And I'm sure you, I just want to make sure I'm on the same page with you, Mike. So here, here is actually for the petawatt laser. This is interesting because this is, oh, the quantum coffee, yes, I like that. So this is actually to make a laser like that. You can see how big this facility is if we look over here, because that is a person. So this is the laser. Hey, Jason. Is that, no, it's actually, so a picosecond, good question. Sorry if you just walked in. Quantum is but it's a defined bunch. So quantum is a defined bunch of something. You are smart, Jason. Not only that, you're also awesome for working out today. So that's great. So this is the petawatt laser, and the picosecond refers to, actually we can come back here. The picosecond, this is a femtosecond that we drew here, but it's a fraction of a second, and a picosecond would be right here, and that would be 10 to the minus 12 seconds. So it's 1,000 times slower than this 10 to the minus 15, this millionth of a billionth of a second. Yes, it doesn't have a purpose apart from science. I would think science is everything. I don't know what exists apart from science from my I guess biased point of view. So he is indeed, yeah. Absolutely, yeah. Oh, lasers, we can talk about applications of lasers in general. So this studies all sorts of things. You can study these very, very high, oh, I see. Yeah, so you can study what happens because, for instance, in the early universe, weapons are one way, yep. For instance, in the early universe, though, a lot of these reactions happened so quickly, so we don't understand a lot of what happened in the early universe, and so this can be a way to help us understand that by by kind of designing a system that will simulate some of the situations of the early universe, for instance. So that's one, and so yeah. So this is the size of the facility, and this is the layout in Texas. I thought this was kind of a cool picture. So my office was kind of over here, and hi, Orion, welcome. And so they call this the laser bay, and most of the laser stuff goes on here, and this is the target area. This is where they study the stuff they want to study. Oh, no problem. Thanks for asking, Zebra. Oh, absolutely love the questions, as always. Transmission of a whole library of computers, 1,000 times a second. Yes! Wow! What transmission of, is that one of the applications that I guess I'm not aware of and not including? Oh, I see. Any possible laser defense? Yes. So, and lasers, yeah, absolutely, for skin treatment. So, and the interesting, and cancer, and other medical treatments are really useful because this not so much, well, so the pulse lasers also, but oh, is this built for, no, this is built, the most powerful lasers that are built currently for weapons are a little bit less. Let's see, I think it was in this one. Here we go, rough comparison. A kilowatt, so this is 50,000 versus a petawatt is gonna be, let's see, that's 3, 4, 5, 12, it's gonna be 10,000 times weaker, I think. I think I did that quick, approximately, but it's a lot weaker, but it is, again, the wattage is a little bit, it can be a little confusing, I suppose, because of that energy and time aspect when you pulse it. But they've put laser systems on weapons already to shoot down like missiles and things like that from a distance. It's pretty cool. They put these things on planes. And actually, when Mike was asking that question about can you, you know, how important is that mirror distance? That it's incredibly important and it's incredibly sensitive. So a difficult one thing that's difficult is, oh, that's a really cool picture too of their laser. One thing that's really difficult is keeping those mirrors in the same spot once you've put them where they need to be. And oh, thank you, Orion. That's very sweet. Good for you for getting work done. So the actual huge systems like this, or not even huge systems, but just to keep these mirrors in the same spot to support these waves on the front of a 747 is just unbelievable. I mean, it's crazy to me. So that's just, it's absolutely crazy that you can hold these two mirrors and they have to be, and think about the precision that you need is on the order of the wavelength of light, and the wavelength of light for these systems. So, for instance, the infrared lasers that are even used in a lot of medical procedures, or those are usually used more in medical procedures. The higher energy lasers, those wavelengths are in nanometers, and so that's going to be, let's see, so it's going to be 1,000 times smaller than the width of the average human hair. So to make these mirrors precisely aligned enough to support something that if you change it by the distance of 1,000 times smaller than the width of your hair, then it won't actually laze properly. So what are the latest on lasers used for optical immunity? Oh, there's a lot being done there because, and that's actually more related to the research that I did, because the plasmonics, the world of plasmonics, is just talking about how to use lasers, well, mostly using lasers, not always, to excite electrons. And so that's kind of like a bridge between light and electricity, using light information and electricity information, because the light energy is then being transferred into electrical energy, or electrons moving, really. Electrons moving, but in such a way it's not actually as slow as electricity. These plasmons are really really cool because they're a little different. And so it's like I've described it, I think, before, on a pond. You can imagine how long does it take for a droplet of water on one side of the pond to move to the other side of the pond. That's electricity. Versus if you throw a pebble, how long does it take for one of the ripples of the wave to travel all the way to the other end of the pond? That's a lot faster. So it's not that actual molecule of water, it's the energy of the wave that goes all the way to the end. So don't sneeze around laser. Do not, yeah, because then you, absolutely right, actually. Getting dust in lasers is a big deal and a pain in the neck. Getting really like smudges. If anyone's seen Real Genius, the movie from, what, 1986 or 7 with Val Kilmer, filmed at Caltech, actually. Always make sure your optics are clean. They smudge the mirror and to sabotage the experiment, and that is absolutely the worst thing you can imagine. You have to clean your mirrors all the time for these lasers, because the precision you need is quite high. So yeah, it's a great movie. So that's kind of keeping in discussion with lasers. What anyone else have any questions before? I think I was just going to talk about the different types of materials. So you get into the diode lasers that are getting smaller and smaller, and that's where you can also think about being used in computing systems more often. So no, Ian, absolutely. Yeah, you have to be, because trust, it is a pain in the neck if you have to replace something, realign something. It's not fun. So any possible laser defense for airline pilots? Oh yes, you asked me that. Sorry. So yes. Oh, absolutely. Go ahead, Ashley, and if I don't answer it or if I forget about it, please tweet it to me. So for defense, plasmonics is actually something that's been looked at for defense for a long time, because that will take something like a laser light, right, and it will absorb it, and it will make it into the energy of electrons that no longer radiate and send off that light that might be dangerous. So now in glass, it depends on the energy. Glass actually will scatter or absorb any of the higher energy stuff. So blue, purple, they have purple laser pointers now, which are so distracting in my opinion. But red laser pointers are a little harder because they're longer wavelength, they don't scatter as easily. It's why the sky is blue, right? The sky is blue because blue light has that smaller wavelength, and then it has a lot easier time in like just running into things and bouncing off. And that's what we see, is that scatters off of the molecules that are in our atmosphere, and that's that gives us the blue sky. So in yeah, absolutely, and it's illegal, but you do not want to point, please do not, for the safety of pilots, please do not point lasers up. If you have a laser pointer outside, you give kids laser pointers, you know, it's not just be careful of your own eyes, it's be careful of pointing them up, because laser light, it doesn't stop right until it runs into something. Thoughts about nuclear power plants? Was that the question? It's about science by an Ant-Man. Oh, my comic knowledge is still quite limited, so I actually don't know what I don't know where to start with that, Ashley, but I'll look it up for you, because I definitely don't, I couldn't even, yes, I will, thanks. So, oh, I'm sorry, and I missed the comment before that, but what color lasers are the most powerful? Ah, hey, yes, I haven't seen you in a while, Ascendant. This movie I see. So, what color are the most powerful? Well, power, it's that's a little tricky to answer because power, for instance, in the petawatt, here, I'll flip it around again. So in the petawatt laser here, or now this 2 petawatt laser in Japan, the actual energy of that thing is not a lot, but it's concentrated in a very, very short amount of time. And so that's what gives it this huge power. And that is a range of colors. So the fact that you have to actually use lots of colors at once to give you a very short pulse. So that laser, that's a laser that's not always on. Those are the most powerful lasers, but you actually have many colors. So that, or you can have different ranges of colors, and then that'll also depend on how quickly you can kind of or how well you can overlap these, and how quickly the pulses will burst, and then how best you can concentrate that energy in time. So, oh, Scott, did you ask a question? I'm sorry if I missed it. Oh, you're talking about the comic, maybe the Ant-Man again. But this white laser that they made is very cool because it's not a pulse. It's just the fact that they've used lots of different materials in one little cavity, and no, it's not dumb at all. Actually, I think if you relate science to something that you're already interested in, that's the only way to do science. So, so this was interesting because this white laser that came out is not a pulsed laser, and it uses lots of these different materials to produce the light, instead of kind of doing this sacrifice of, okay, we'll only have the laser on for a little bit of time, and then you have lots of colors overlapped in one. So, great, yeah, excuse me. So in general, in terms of light, just any light, not necessarily laser light, but if you're just talking pure light here, oh, and I learned I can just expand this if I need to, huh? So if we're talking about just light, not laser light, but in general, then you're absolutely right. So if we draw the wave of light, and the analogy I've made before, oh, the nuclear fusion reaction. Are you talking about the 100 laser system that's trying to produce fusion? I think it's awesome and very cool. But if you have any specific questions, I'd be happy to answer them. So this would be, for instance, red light, and then this would be blue light. And I draw the wavelength as shorter for blue because it has more energy. So blue on the spectrum, on the visible spectrum, the shorter the wavelength will always have more energy. Hey, Julia, nice to see you. So the energy here, the analogy I make is like if you attach a rope to a wall and you want to shake it to put different to put these oscillations in it, these waves in it, then how much energy do you have to put into that rope to have only a few of these waves or have a whole bunch of them? And so if you have a whole bunch, if you want a whole bunch of them, you have to put a lot more energy in it, right? And that's kind of why the blue light, which has a shorter wavelength, has more energy in it. And that's why something like UV, ultraviolet light, will burn your skin because that has a lot more energy than the red light in Sam's darkroom, for instance. And that's also why it doesn't, that's why your darkroom is usually, why it's red. It's because that red light, this longer wavelength, has less energy and is not going to stimulate those reactions in the chemicals to develop or fix the film. And so, oh no, that's fine, no problem. Is it, I want to make sure, is it Dan's? Yes, it is Dan. Oh, I'm getting better at it. So, it will, exactly right. Yeah, exactly right, Valerie. It'll sanitize water because this high energy will blast apart some of these microbes or bacteria that are in the water and not safe to drink. So, thank you. Yeah, I'm getting better, getting better. So, in general, if you're just talking about light, and it is the International Year of Light, here, I'll bring this back, International Year of Light, and you can go to either of these websites for some cool information. But yeah, these, oh, Sam, maybe you weren't here if you missed it. I was talking about your darkroom. So in general light, not necessarily laser light, but just in general light, this is definitely a property of light. The longer wavelength, the lower energy, sorry, on which end of the spectrum does the wavelength get shorter? Oh, that will be the high end. So if you do the visible spectrum, for instance, then we have red here, and then blue and then UV here, and this would be lower energy, and this would be higher energy. Yeah, exactly, yeah, so UV is the higher energy end of the spectrum, sorry. So, and Sam, your dark room, I was saying your dark room is red because that lower energy light is not going to hurt your film and cause those chemical reactions that develop the film when you don't want it to happen, right? So you go into a dark room, it's always going to have that red light, whereas the UV light and the blue light that you're exposing the film to for the actual image, that's what's causing the chemical reactions in the film, in the whatever the film is that you're using. And I was actually wondering, Sam, if you've ever used palladium. That was because I think you were talking about silver nitrate. So anyway, so that's light in general, and thank you for asking that question. So the other, oh, my board's going crazy here. So the other applications here are different types of lasers. There's so many different types of lasers. It's really kind of hard to do a nice overview of all of them. Oh, okay, cool. Maybe I'll see if I can find out some of that information, because I don't know much about it. I just know that it was used at some point in photography. So this is the petawatt. This is a huge laser, and then you can have tiny, tiny lasers that are. So ultraviolet ovens would cook faster. Ah, great question, Mike. So actually, that's interesting. So not necessarily, and in just relating to microwaves, no, because microwaves, the way that they work is the wavelength that's used is resonant. So that means it is, for anyone who doesn't, maybe you're not familiar with resonant, but if you think of, oh, I'm sorry, private message. I thought I opened that up, or, let's see. Well, I'll see if I can fix that. I'm sorry, Valerie. But I'll send you a message, or I'll try that way too. But a microwave actually is exactly, a tuning fork. Or if you've played a guitar, there's 2 E strings. If you hit one E string, it'll actually make the other E string vibrate a little bit. And that's because it's a harmonic. It's a harmonic of that wavelength, so it's a multiple of that wavelength. So a microwave is working because the water molecules, the energy of the rotation of the water molecules, is resonant with the wavelength that a microwave uses. And that's actually why you have a defrost button as well, because ice has a different resonance than liquid water. And so the UV would actually not help you so much. It would be heating it, but it would be heating it in a different way, and I don't know that that would be, in fact, probably not more efficient, because to produce that high energy light, you're going to need more wattage or voltage from the wall. So the resonance aspect is really how that microwave is just awesome. Are microwaves dangerous? Well, they are if you get inside one, but otherwise, no. They're not dangerous, for instance, if you stand in front of one. I'm glad I could give some sort of tidbits here. And so yeah, if you stand in front of a microwave, it's actually not dangerous at all, and that plastic in front of it doesn't do anything. The thing that's really protecting you is a mesh of wire, and the metal is really it's called a Faraday cage, and it's usually why in most elevators your phone will stop working, is because you're in a big metal box, and that contains electromagnetic radiation, which is what the microwave, what light is, what the microwave is producing to excite all that water. So it's that if you look closely on a microwave, even when it's not working, right, if you look at the window, it's got a very fine mesh of wire in it, and that mesh is really what's keeping the waves in that box, and not the plastic at all. But because a lot of people had issues when they first came out with microwaves, they felt unsafe because you could see, there was the air getting through, so they put that plastic on there. What material? Good question. I don't know. Probably aluminum, because it's cheap, I would imagine. But really any metal, any conductive metal. Copper's probably a little too expensive for it to be used for. So yeah, so hopefully that was pretty cool. So if there are any other questions about lasers, or if you want me to talk about any specific type of laser, please let me know. Tweet me. We can talk about that definitely more often. Tomorrow is Fractal Friday, and tomorrow is actually going to be on the road. I am traveling. I am leaving today to go to Portland, and I'm going to see the next week or so a couple of possible Portland Periscopers, so that I'm really excited to meet. So I've known them for a couple months now on this app, so I'm gonna get to see them out there as well as see some wonderful friends. So thank you. So tomorrow will be Fractal Friday, but on the road, and I can answer any other questions on Twitter or on the website. I'll put some of these links up about lasers if you have any questions about them. So thank you again, everyone. Thank you so much for joining. And oh, I will. Ashley, where? Oh, I didn't know how close. Where are you? Are new mothers of, or are there new methods of producing photons? Well, yeah, of course. Producing photons, I'm not sure about. I think there are new methods all the time, but it's not. I'll miss. Oh, no worries, Linda. Thank you. And speaking of Linda, you can follow Linda and learn how to make these awesome Nanda bands for the kids in Brazil. So. Oh, you're 5 hours north. Oh, well, what a shame, because we're actually visiting friends that are 4 hours south. But if you're in Portland, I'll be there for a couple of weeks. So I would love to meet you, Ashley. That would be fantastic. But of course, Linda, yeah, for sure. So Linda will be knitting here in half an hour or so. Ooh, I went late today. So you can find her daily lessons. Nanda bands for the win. So this poor kid, well, as I said, it's kind of okay. I'll probably try to do a better one. Thank you, everybody. Indeed, Portland, Oregon. So thank you, Dan. Have a wonderful rest of your day, and I'll try to upload all 3 of these laser sections by the end of the week. Happy science, indeed. Oh, thank you so much. Oh, thank you. Yeah, they tend to do that for me as well. Music. They've some of them are great, some of them are not so great, but. If I can help make it interesting, then that brightens my day for sure. Have a wonderful day. Thanks, Ashley. Thanks, everybody.